Hi everyone. We started discussing on Tuesday's class question number 8, which you were asked to calculate the probability of being dealt a 3 of a kind and 3 cards of the same value and 2 cards that are of 2 other different values. So when we began discussing this in class today, I suppose it would have been helpful for me to underline the key pieces of the problem, because when I read the question, I interpreted it as 3 of a kind, and then the other 2 cards had to be also the same value, that is what consists of a full house. Okay, so it would have been helpful if I would have underlined or highlighted the fact that the 2 other cards in your hand have to have different values. Okay, so I'm assuming, based on what we talked about in class, that you guys should know what it means to be 3 of a kind. Okay, we have 5 cards that we are going to be dealt out of 52 cards in a standard deck. So this part is 52 combinations of 5. We are going to first calculate how many different 5-card hands I can be dealt from a deck of 52. If I type into my calculator 52 combinations of 5, this would give me 2,598,960. So we had that part correct in class. The total number of 5-card hands is 2,598,960. So the next part of the problem is we're going to calculate how many different ways from a deck I can get a 3 of a kind. Okay, so first of all, we're going to have to choose our 3 of a kind. We're going to have to choose a number for 3 of a kind. So am I going to get 3 aces? Am I going to get 3 twos? Am I going to get 3 threes, 3 fours, 3 fives, 3 sixes, all the way up through kings? So in a deck of cards, you have an ace, which could, depending on the card game you're playing, could count as a 1 or an 11, I guess, in certain games. 2, 3, 4, 5, 6, 7s, 8s, 9s, 10s, jack, queen, and then kings. So if you count this, there are 13 different face cards that you could get. There's 13 different faces on the card. Thus, we have 13 choices for our 3 of a kind. There's 13 different ways, 13 different numbers I can pick from this list to choose my 3 of a kind. Now, once we've chosen the number, so for instance, 2s, you have 4 of each of these numbers in a deck, right? There's 4 aces, 4 2s, 4 3s, 4 4s, 4 5s, 4 6s, 4 7s, 4 8s, 4 9s, 4 10s, 4 jacks, 4 queens, and 4 kings. And if you added all those 4s up together, you would get 52 cards, because 4 times 13 is 52. Now, here's the thing. Once I've selected one of these 13 numbers to be my 3 of a kind, so I'm going to have like 3 kings or 3 queens or 3 jacks, now I have to pick how many different ways can I select those 3 cards from the kings, from the queens, from the jacks, or 10s, 9s, 8s, so on. So we need to figure out how many different ways we can choose 3 of that kind. So let's just, for an example's sake, let's say our 3 of a kind is going to be 6s, right? Let's just say our 3 of a kind is going to be 6s. Then there are many different ways I can choose 3 of those 6s from the group of 4, because there's 4 6s in the deck, and I need to choose 3 of them for my 3 of a kind. So if I do 4 combinations of 3, that will give me 4 different ways that I could choose 3 of those 6s from the deck. Okay, So to find out the number of three-of-a-kind hands we can produce, the number of three-of-a-kind hands that we can produce, if I scroll this up a little bit, total number of three-of-a-kind hands that you can get from a 52 card deck is 13 times 4. So if I multiply 13, because there's 13 different numbers to choose from, and once I've chosen my number, for instance, I said, what if we chose 6, then we still have 4 combinations of 3, because we have 4 6s in the deck, and we need to choose 3 of them, and there's 4 ways to do that. So by using the fundamental counting principle, there's 13 ways to choose a face value, and then there's 4 ways, once we've chosen that face value, there's 4 ways to take 3 of those cards. That would give me 52, right? So there's 52 different three-of-a-kind hands you can get from a standard deck of cards. So now we said we're going to have a 5-card hand, right? And we said that the 2 other cards, it does not matter, they do not have to be the same. Okay, I interpreted in class that those 2 cards had to be the same, which would be a full house. Okay, that's an entirely different problem. Almost the exact same problem, but slightly different at the end. This next part would be different for a full house. However, on the next slide, I'm going to describe how we are going to choose those other 2 cards. So far, we have our 3-of-a-kind. There's 52 different ways we can get our 3-of-a-kind. And in the next slide, I'm going to explain to you how we're going to get the how many different ways we could fill those other 2 card slots. Okay, so we've decided that 3-of-a-kind, there's 52 different ways we can get a 3-of-a-kind. Now, my other 2 cards, right, we said on the last slide, we have ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, not 11, that's a jack, queen, and king. Okay, so we had 13 different face values in a deck of cards. However, I used in my last slide, I said, let's just say the 3-of-a-kind was a 6, right? Okay, so I have to cross off one of my options. I don't care what my 3-of-a-kind was, but I'm just sticking with 6 because I used that in the last example. So once I've chosen my 3-of-a-kind, I have to cross off one of the face values from this list, which leaves me with 12 choices. So here's the deal. I have 12 choices, and I want to choose 2 of these numbers because I do not want the cards to be the same. And that is where I read the question wrong in class today, because I was going to do 12 combinations of 1, because in a full house, those 2 cards have to be the same. In this example, they don't want those cards to be the same, so I have 2 choices from the remaining values up here, right? And there's 12 choices, and we're going to choose 2 of them. So if I take 12, choose 2, I get 66 different ways to choose 2 cards. To choose 2 of these face values, I have 12 different choices to choose 2 different face values from those cards. Okay, there's 66 ways to do that. Now, because I don't want the cards to be the same, the 2 slots, I have 4 choose 1 and 4 choose 1 again, because let's say for the last 2 slots, I'm going to pick a 2 and a 10. Okay, so my hand of a 3-of-a-kind is 6, 6, 6, and no, I wasn't purposely doing 6, 6, 6 there. But I am in this question because I said that we already used 6 as our 3-of-a-kind. And so these 2 slots have to be different numbers right here. These 2 slots cannot be the same number. But I am going to pick two numbers from this list, and we figured out we had 66 ways to do that. Once I choose what numbers are going to be here and here, so let's say a 2 and a 5, right? There is 4 2s in my deck, right? The number of 2s in my deck is 4, and I only want to take one of them. So there are 4 different ways I can pick a 2, and there are, if I'm going to use 10 as my other value, why did I put a 5 up here? This should have been a 10. I would have 4 different ways to select a 10, right? So there's 4 10s in the deck, and I am only going to take one of them. So my hand is 3 6s, a 2, and a 10. A 3 of a kind, and the last 2 cards cannot be the same. Okay, so there's 16 different ways I can pick a 2 or a 10 to fill those last slots, and there's 66 ways that I can, from these 12 choices that were remaining after I picked my 3 of a kind, that I picked 2 different face values. So what I'm going to do is the number of ways I can fill these last 2 slots here, again, this was just a sample or an example, but the number of ways I can get fill these last 2 slots is 66 times 16. So if I multiply 66 and 16, I get 1,056. Okay, so now that I know the number of ways I can fill the last 2 slots, right, so that they have a different face value, I'm going to take that answer and take it and multiply it by the number of ways I can get my 3 of a kind, and that will give me the total number of ways I can get a 3 of a kind and then fill the last 2 slots with different cards. And I'm going to calculate that on the next slide. So we've just decided that the number of ways to get a 3 of a kind is 52 different ways, and the number of ways to fill the last 2 cards that are different face values, they can't be the same number. There is 1,056 ways to do that. So the number of ways to get 3 of a kind and the last 2 cards a different value is going to be, if I multiply those 2 numbers, you get 54,912. Now remember, that's the number of ways I can get 3 of a kind and the last 2 cards to be a different number. And to find the probability that that occurs, I have to divide that by the total number of 5 card hands that you can get from a 52 card deck, which is 2,598,960. So this is our final answer, and it's the one that matches the answer key. So we have now found the correct answer to number 8.